Hello, and welcome to Game Theory. I'm Professor Naomi Utkoff of the United States Naval Academy. In this second of two videos about Bertrand Duopoly, we'll study a Bertrand model with asymmetric costs and finally arrive at a game with no Nash equilibrium. Now we will consider a model of Bertrand competition in which the firms competing have different constant average and marginal costs of production. As in our first video about Bertrand competition, firms simultaneously and independently announce their prices. If one firm's price is lower than the other firm's price, consumers go to the firm with the lower price. If the firms name identical prices, then the firms split the market. The important difference from our previous video is that firm 1's constant average and marginal cost of production is 10, while firm 2's constant average and marginal cost of production is now 20. In contrast, our first video about Bertrand Duopoly presented a model in which the firm's costs were identical. As in the previous video, we considered two versions of this now asymmetric game. In the first, prices must be whole dollars. In the second, we allow any non-negative price. We'll find a Nash equilibrium in version 1 and show that there is no Nash equilibrium in version 2. First, we'll consider the game with whole dollar prices only. Recall Bertrand's basic premise. Given the opportunity, firms will undercut each other until no more undercutting is possible. Firm 2's cost of production is higher, so at some point, firm 1 undercuts firm 2, and firm 2 cannot profitably undercut firm 1 and responds. Suppose P1 equals 19 and P2 equals 20. We'll start by showing that firm 1 doesn't have a profitable deviation. Certainly, it doesn't want to raise its price and either share the market with, or worse, cede the market to, firm 2. On the other hand, firm 1 certainly doesn't want to lower its price because that would reduce firm 1's profit. P1 equals 19 is therefore a best response to P2 equals 20. Now, we'll show that firm 2 doesn't have a profitable deviation. Certainly, raising its price is not a profitable deviation, since at P2 equals 20 or more, firm 2's profit is still 0. On the other hand, firm 2 certainly doesn't want to lower its price, because doing so would result in negative profit. Therefore, P2 equals 20 is a best response to P1 equals 19. P1 equals 19 and P2 equals 20 is not the only Nash equilibrium of this game, but we'll leave the argument here. Now, all game theory heck shall break loose. We'll allow the firms to select any non-negative price. $10.27, $9.99, the square root of 211, you name it. Let's show that this game doesn't have a Nash equilibrium. First, we'll show that there isn't a Nash equilibrium in which P2 is less than or equal to 10. If firm 2 chooses P2 less than or equal to 10, firm 1 best responds to firm 2 by choosing a P1 greater than or equal to 10. Firm 2, however, is not best responding to firm 1. It is now earning negative profit, but could earn 0 profit by deviating to P2 equals 20. So, if there is a Nash equilibrium in version 2, P2 must be greater than 10. However, firm 1 has no best response to such a P2. If firm 1 chooses P1 equal to 10, it earns 0 profit. Firm 1 can profitably deviate to P1 prime greater than 10 but less than P2 and earn positive profit. However, P1 prime is still not a best response to P2, since firm 1 can profitably deviate from P1 prime to P1 prime prime greater than P1 prime but less than P2. This process doesn't stop, so firm 1 has no best response to P2 greater than or equal to 10. So here we are, a game with no Nash equilibrium. You might be thinking there's a mixed strategy Nash equilibrium out there, but there is not. We'll leave that one as a proverbial exercise for the reader. Thanks so much for watching this video about Bertrand Duopoly with asymmetric costs, in which we finally landed upon a game with no Nash equilibrium. In the next video, we'll state the Nash existence theorem, give several examples of its use, and a flavor of its proof.